Hello. We're going to speak today about the auditory nervous system. And before we start speaking about it, I'm going to give you an overview of the entire auditory system. The auditory system generally is the system that enables us to develop many kinds of skills, and the most important one, of course, is auditory perception, which is the ability to make sense of the sounds that we hear and to kind of connect them to build concepts, linguistic concepts and concepts that we encounter in the world. And it enables us to develop working memory for speech, so that you will be able to remember sounds and to remember words and sentences and things that you hear and hold them in your memory while you are thinking about them or processing them. And also, it enables us to retrieve linguistic information. So the auditory system is the channel for developing language. And without the auditory system, the person will not be able to speak verbally, to communicate verbally, even though they can make sounds, for example, like they can scream, they can make all kinds of sounds, but they will not be able to produce speech if they do not have the auditory system, or if they do not have the stimulation, the linguistic stimulation that enables them to develop the pathways along the auditory system. So this system is really important for contributing to the development of our various perceptual abilities and language, cognition, and thought processes, and you name it. For this reason, you need to understand the basic and emphasize the basic anatomic structure and the functions of the auditory system. So don't be too much concerned about the little details. When I teach this class, I teach it based on different levels. And if there's a class that requires more information, I would provide the information according to your needs. So the auditory system is generally divided into two divisions. One is the peripheral auditory system, and that is the outer ear, including the pinna that you see outside, the ear canal, and the outer ear, and the middle ear includes it is the chamber that is inside of the bone that's known as the temporal bone. And inside of that chamber, you have three little bones, the smallest bones in the body, called the ossicles. And they are connected in a chain kind of link. And the first one of them is connected onto the tympanic membrane or the eardrum, so that when the sound comes in, hits the eardrum starts to vibrate back and forth. When it does, it's going to make that bone move back and forth the same way to mimic the movement. And that bone is connected to another one, and the second one is connected to a third one. So you don't have to worry about the particular names, but you will have them, in different images, you will see them. And then the important thing is that the last bone that is shaped like a stirrup, that's called the stapes, is connected onto the inner ear. And when you watch the video on auditory transduction, you are going to it will start here. So our main focus here is on the auditory central nervous system. So again, the peripheral nervous system, the peripheral auditory system consists of the outer ear, which is the pinna, and the auditory canal or the external auditory meatus, and the middle ear. The middle ear is, again, it's a chamber that should have air inside of it, and it has the three bones. One is called the malleus, and then the incus, and then the stapes. And so the stapes connects onto the inner ear, and we'll discuss the inner ear in a little bit more detail. Before I move on to the central auditory, the auditory central nervous system, I would like to mention a couple of things that are going to impact functioning of the inner ear and also functioning of the whole system in general. But the third part, the inner ear, is the kind of the link between the outer or the peripheral auditory system and the inner or the central nervous system. So you could see here, out of the cochlea, you have a nerve coming out. That's the auditory nerve. And from that point, the auditory nerve enters the brain stem. And from that point, we speak about central auditory processing. And you know, this is the main focus of this part of this week. So there are a lot of things you need to understand in order to understand people who have hearing loss. First, there are two major categories of hearing losses. Actually, you could say three, but the major two categories are peripheral hearing losses or conductive hearing loss. Conductive hearing loss means you are transmitting information from point A to point B, but along the path there's an obstruction. So you're instead of conducting it, and then there's something that is physically preventing the signal from going through. So we call these problems conductive hearing losses. They are temporary. Of course, they depend on the obstruction. When you move the obstruction, the system is going to take a little bit of time to get back into work. So one of these situations is if the pinna gets injured, or if the pinna, for example, somehow is malformed. That is going to affect your sound, the way that you hear, and then eventually the way that you process sound. The curvature of the pinna, the way it is made, it is to actually receive and to amplify the sound, to make it louder, and to bring it into the ear canal. You notice that it has cartilage, and it is smooth. And that means it doesn't absorb as much sound. It doesn't absorb much of the sound wave, so it contributes more to amplifying it. Then the cone shape of it, the way all these curvatures are made to make the sound louder, because as it goes through, it will face several obstructions, and you want the signal to be optimal. And along the whole system, you have to have things to amplify the signal until the very last second when it goes to the brain itself. I mean, to the cerebral cortex to be processed. So the signal now goes into the ear canal. The ear canal itself is also made in a way as to amplify sound. First, it is a tube that's closed off by the tympanic membrane. So when you have a tube that you close off like this, you are going to find that the sound is going to be different. It will be amplified. And there are many reasons why the ear canal amplifies sound. Number one, it has a big part of it is cartilage. It has smooth walls, and it has that layer of earwax. We know it as cerumen, that makes the surface nice and smooth and shiny, and it plugs, holes and things so that the sound wave would not be absorbed. So in addition to closing that, any tube that you have close off on one end is going to act as a filter. It is going to selectively take out of the sound wave elements that oppose the sound wave and make it compromised. And it will leave the, parts of the sound wave that are, that amplify the sound and add up to the strength of the signal. So I don't want to get into too much, but look at this tube here, for example. When I put a tone into it, when my voice matches the frequency or the pitch of the air inside of the tube, it is going to give me, to resonate the sound, to amplify it significantly. I try to modify my pitch, and when it comes closer to the pitch of the tube, you are going to notice resonance. Means both of them resonate, they kind of are similar, and you get better amplification the closer the pitch is, my pitch, to the pitch of the tube. So let's see. So you could notice now, as I adjusted my pitch, it resonated more when it started to come close to the tube. But anyways, what I wanted to say is the structure of the ear canal is made in order to act as a filter, to number one, to eliminate bad elements of the sound wave that oppose the wave, and to leave the elements that will contribute so that the sound wave will be amplified. Then the signal, when you see now in the ear canal, if there is excessive earwax, then you are going to have obstruction. You'll have conductive hearing loss, which means the signal is not going through. Once that is removed, then the hearing will be okay. However, based on what we know about the critical periods, if that obstruction continues for a long time, like say when a child has frequent middle ear infections, where the middle ear is plugged with fluid and sitting there for months, that is definitely going to affect the sound perception. Even though the research in this area is in its infancy, and you are going to look and find like a lot of research that says there's no significant impact of middle ear infections. That is because the science, the technology is now being understood. It enables us to understand the system better. But I bet that when you look deeper into this and we understand the system more, you will find that many of the sound errors that children develop and the articulation problems they have, they would be attributed to problems that have to do with hearing. I'm not saying that all of them, but at least a significant number of them, or percentage of them. That also definitely contributes to how the auditory maps on the cortex are structures, and we'll discuss this in detail. So it is important to monitor children to see if they have excessive earwax, to take them and to send them to their physician so that they can take out this earwax. And some kids might need a cleaning every month, even some adults, because some people produce more than others. Now, the American Otolaryngology Association once in a while they issue a statement warning the public um, about using Q-tips. The idea is, if you use Q-tips, you are actually stimulating the glands that produce earwax. So it is like someone has a pimple, and the more they touch it, the more they rub it, the more it produces stuff to fill it more, make it bigger. So using the Q-tip, you can feel itself, you can feel it physically as like a nice feeling of tickling. That is, you are inducing release of more wax. And when you do that, as you keep cleaning, the stuff goes inside, goes more. And in some extreme cases, the eardrum could be even punctured. So the best way is not to use Q-tips. And when the person takes a shower, hot shower, of course that melts the excessive earwax naturally, and it's going to make the stuff come down. You see that the ear canal is kind of bending as you go out. It goes lower. It is not as such in children. It tends to be a little bit more horizontal. So children need to be watched. Also, when the ear there's excessive cerumen, like excessive earwax here, in addition to the signal not being able to go as well through to vibrate the tympanic membrane, it is going to affect the ear pressure inside of the middle ear. So in order to have an appropriately functioning tympanic membrane, you must have the air pressure outside, which is in the ear canal, equal to the air pressure inside of the middle ear. And that is going to enable you to have equalized pressure, and it will make it less likely for the person to develop middle ear infections. Because one of the causes of middle ear infection, of the fluid that comes with middle ear infections, is that there will be the pressure will be negative inside of the middle ear because of some abnormalities, and maybe the eustachian tube is not working well, and so on. And that negative pressure creates suction, and that suction pulls the fluid out of the walls of the middle ear, and gradually it creates mist, and that mist becomes fluid, and the fluid builds up and builds up, and it becomes quite a significant thing, and it will stay there. In order to make it go down, you need to open the eustachian tube, and some extreme cases require the insertion of myringotomy tubes or ventilation tubes, where they kind of make them inside of the eardrum. It is similar to the gasoline can that you used to use in your car to fill your car, and you notice it has a little plug button on top that you lift up to allow the air to go in, so that the gas can go out more freely on the other end. That's the whole purpose of the ventilation tube, and it's typically positioned on this corner here, across from the eustachian tube. So middle ear infections or excessive cerumen, these can affect, depending on how long they are, the problem persists, and how frequently the person has it. And now look at a child who is 3 years old. A month in the child who is 3 years old, that is a huge amount of time. Divide 3 years by 1 month, or kind of get a percentage and see how much percent of the 3 years it makes 1 month, and you are going to find that it is not a small problem. So I'll tell you some of the basic signs of children with middle ear infections, so you can identify them. One of them is that the child will be sitting and kind of not paying attention well, and the eyes will have a glaze over them, almost like watery eyes. We call them glassy eyes sometimes. Sometimes the child may be breathing through the mouth, because oftentimes middle ear infections accompany upper respiratory infections, and in many cases the person has adenoid enlargement and tonsil enlargement that are also exacerbated by upper respiratory infections. So when you see a case like this, alert the speech language pathologist in your school or place, and also alert the nurse, and so that they could maybe check the ears and see if there is excessive earwax, or if the nurse will tell you if there are signs of middle ear infections, and then they can take it from there. So peripheral hearing losses are curable. Anything that can happen, even the outer, the ear, the pinna here, can be totally reconstructed. They have procedures where they take cells and they implant create take a piece and shape it and open the person's hand here, and they embed the tissue and make it grow into an ear, and then they open up and take it, and then they put it there, so it will be the person's natural ear that they implant later. So that could be reconstructed. The ear canal or any problems in the ossicles, they can even be implanted. For the person, if they are not functioning, you can get devices that replace them. So all these conductive problems are curable. However, sensory neural problems that are caused because of the cochlea, mostly in the cochlea, the inner ear, these are not reversible. They are not curable. We use means to make the person hear. For example, like cochlear implants, like hearing aids, amplifying, FM systems. However, nothing equals the natural sound. The natural cochlea, as it transmits signals in various levels and various pitch levels and so on. So let's look now. You see I posted a brief video that it describes and tells you how the sound is processed through the cochlea, and you'll find it really, really nice, and it's quite informative. So inside of the cochlea there is fluid, and there are 3 chambers that you will see in the video, and as the signal goes, the stapes that is here is connected on this window called the oval window, and when the sound wave comes in, it pushes the stapes into the oval window, and that makes the wave makes it repeated in the fluid all along the levels of the cochlea, and that is going to shake the hair cells inside of the cochlea, so they will bend like weeds in a stream as the signal keeps going, and when the signal stops, they come back again. So they keep going back and forth. Every time they bend, they cause the firing of a signal that travels through the auditory nerve. And you see that again in the video. It makes it really animated and very clear. Next to the cochlea, of course, is the vestibular system that has to do with our balance, and we usually do not spend too much time on it because our focus is on the auditory system. So all the fibers that connect on the hair cells, each fiber becomes part of the auditory nerve, and all of these fibers exit, and they are all kind of bundled together into a big bundle called the cochlear nerve or the auditory nerve. And on the other side, the vestibular system, your balance system, all the fibers are again bundled up into the vestibular nerve. And then the vestibular nerve and the cochlear nerve are bundled together into a bigger, nerve that goes into the brain stem, and that is called the vestibulocochlear nerve. And of course, balance is related to hearing, but we don't have to go through any of them. So these are hair cells. Underneath, let me show. You could see in this image here, this area is when you take the cochlea and imagine that, say, for example, that instead of the spiral shape of the cochlea, imagine that you create one out of dough and then unwind it and make it long and just cut it transversely, and you look inside of it like this. You are going to find that it has 3 chambers, and in the middle chamber you are going to find this structure called the organ of Corti, and it has hair cells, the body of a hair cells, and that body of the hair cell, there are 3 rows called the outer hair cells, and there's 1 row called the inner hair cells. So you could imagine them, say for example, the cochlea like a spiral staircase, and on every step of the spiral staircase you have 4 rows, every single step. And you have 3 rows near the stairwell, and you have a gap, and you have 1 row near the outside wall of the staircase. And as you keep, every single step of the staircase has that same structure, so you end up having 1 single row of outer hair cells going all to the very top, and then you have 3 other rows going up to all the way up to the top. So the hair cell, on one end, it is connected on average to 2 nerve fibers that exit the cochlea to become part of the auditory nerve. And on top of the hair cell, so that body of the hair cell is buried in the tissue, and on top there are little extensions like little hairs called the stereocilia. These are the ones that we call hair cells, and they are suspended in the fluid, and on top of them they have a membrane connected, like a sheet of cellophane connected on all of them. And when that membrane moves down and back and forth, it's going to cause the shearing of these stereocilia. They bend. Every time they bend to a certain level, they are going to activate firing inside of the body of the cell. That firing goes through the auditory nerve, and eventually all of that is going to go to the cerebral cortex, the auditory cortex above your ears. So for the majority of cases, sensorineural hearing loss results from damage to the hair cells, especially damage to the stereocilia. They die. And one of the reasons that they die is excessive noise exposure. So when you see children, you see adults, an average university individual, when using earbuds, or earphones and walking around and listening. Um, Harvard conducted a study a few years ago, and it showed that students, the average college student, has about a 15 to like 20 decibel hearing loss, like a mild hearing loss. Now, add to this, these are young people. Add to this that as we grow, our hearing also deteriorates. So these people who start their lives with a hearing loss already, we are speaking about an irreversible hearing loss. So, these people who start like that, they are going to be at a disadvantage. They will be at a risk for having a more significant hearing loss as they age. Now imagine when very young children are listening to these devices, and frequently they are going to be at at risk for a worse hearing loss as they grow. One big part of the what audiologists do is prevention of hearing losses, because we should not take it for granted. Working in a noisy environment is going to make your, constantly is going to make your hearing worse, and these are not reversible hearing losses. So we should discourage as much as we possibly can the children from using earbuds and headphones for excessive amounts of time, and inform parents about the risk of noise-induced hearing loss. You know that even physicians using this stethoscope for 15 years, they on average lose 5 decibels. So they would have a hear, and they don't like sit there listening for hours. No, they do it, like based on the case, but it's not like sustained, like listening to the device for a number of hours a day or a number of hours a week. Yet that is going to have an impact on their hearing. Also, ultrasound. When pregnant women go to have an ultrasound, especially in the last trimester, when this auditory system, the cochlea is developed. The noise that was produced by the ultrasound is equivalent, at least, based on the 10 years ago studies, it is equivalent to a train passing over a tunnel. Like you are in a tunnel, and right above your head a train is passing. The noise is equivalent to that for a baby in the womb. So frequent ultrasounds for babies do put the child at risk for being born with a hearing loss, or with a hearing that is not as it should be at birth. So that's one area, again, that we need to watch for, that we can develop recommendations, and to warn parents and inform teachers that we want to protect our children against noise exposure, so that their hearing, that they have intact hearing. And you can imagine, of course, joining the band and not using appropriate ear protection, working in again noisy environments, and all of this, that is going to have an impact. So on the surface, so beneath, these are the stereocilia. Beneath, you will find the body of the hair cell itself, and these are like the little weeds in the stream. As the sound wave comes in, it makes them bend over and they come back and go back and forth. But if they are exposed to frequent noise exposure, like someone working in a factory for a number of hours and they're not protecting their ears and the noise level is high, these weeds in the stream will have no chance of just staying up, going back like this, regaining their stature like this. They will be like this, and over time they will not be able to stand up again. It's like if someone walks around with a bent shoulders for several months, they will develop a humpback. So it is again, I just to enable us to inform parents and caregivers and teachers and about the danger of noise-induced hearing loss. The auditory central nervous system has to do with the auditory nerve, the pathways inside of the brain stem, and the part of the cortex that is known as the primary auditory cortex. So the auditory system in general is very important for survival, obviously communication, and also enabling us to hear signals of things that are moving around us. Imagine someone who cannot hear and is walking down the street in a busy area. They will be at risk for being hit by a car because they can't hear the noise at all. So it's again a tool for survival. You will if you watch this video, it shows an owl, how it uses sound and how it localizes sound, and it catches prey under the ice based on the sound. But the reason I put this video up there is that it shows us how the owl localizes sound, how it can identify where the sound is coming from, the angle. Is it like 70 degrees to the left? Is it 55 degrees to the right? The angle of the sound and the vertical kind of plane of the sound. Is the sound coming from a lower area, a mid area, a higher area? So you end up having this. You end up having that the X where the pilot is, for example, wants to shoot a target, and you get that X and just hone it and put it on the target and exactly pinpoint it with laser accuracy. This is how the auditory nervous system works, how it actually enables us to pinpoint the location of the sound and very, very accurately. So the auditory system is a primary tool for human communication, and it is also the primary tool for developing auditory perception. Auditory perception is being aware of the sound signals that you are receiving and understanding what they mean and connecting them to your background knowledge, so that the previous sounds that you have memories for, that that you associate them with different things. So that is the tool for developing auditory perception. Sound localization, sound identification. This is a multi-step process that mostly takes place inside of the brainstem. And along the brainstem there are pathways arising. These are called the ascending pathways. When we say ascending, always we mean sensory. It brings sensory information, either hearing or touch or whatever it is, and it sends that up to the cortex so that the cortex can make sense of it. When we say descending, we speak about pathways that come down either to provide feedback and to regulate functioning of lower areas, basically to give commands from the cortex to lower structures. So the localization of sound, being able to pinpoint the angle of the sound, where it is coming, like left or right or in front of you or back and so on, and exactly is it up or down. Just pinpoint the sound and identify it. The horizontal scanning piece requires two functional ears, two functional pinnae, ear canals, and two functional ears. And we'll explain why that is the case. And the vertical scanning, vertical identification of the sound can be performed by a single ear. So the auditory system, in order to detect, horizontally where the sound is coming from, first, Speech and Hearing 101 tells us that when you hear a sound, when the sound source is ahead of you, exactly vertical ahead of you, that sound signal is at the maximum amplitude, the maximum level. Now, I know that you might be thinking now, oh, this is why they tell students preferential seating and 6 feet away from the teacher up front and all of this. That is ideal, of course, but dynamic teachers do not stay in one place. So it makes it tricky. But just to, again, that is one of these strategies we say preferential seating. You have to keep in mind where your location is and where the student is. The student doesn't really have to be up front. If you are moving, you can just move closer to the student. You look and face the child directly, and that is going to make the sound wave optimal, 100%. So when you when you hear a sound that's coming 90 degrees, face to face, 90 degrees, whether front or back, that is the same. If you split the space into front and back, you are going to find that it is only 180 degrees. Up in front of you 180, back of you is 180, and they are identical. Like a sound coming from the back, facing the center of your head from the back, your ears, both right and left, are gonna hear the sound at the same time. And in front of you, the same. But once your head changes a little bit, now you have an angle. The ear that is closer to the sound source is going to hear the signal first. And then the other one is going to go around, and it will be deflected against the face, so in the case of high-pitched sounds, and it will go and cover a bigger distance to come over here. So if you make two lines, one from this ear to the laptop and one from this ear to the laptop, you're going to have a triangle with one side that is shorter than the other. And systems inside of the brainstem are going to measure now the difference between the time it took for the signal to reach the right ear and the time it took it to reach the other ear. And calculating the difference is going to give us lots of... So the difference between the time it took the signal to come to this ear and the time it took the signal to go to the other ear is used basically and integrated with the pressure wave itself and the strength of the wave and the energy in the wave itself to basically calculate the wavelength, how long the wave is, and how far, when you calculate the wavelength, you can actually calculate the distance as well. And it's a very neat system, and it eventually, when you calculate the difference between one ear and the other, you you identify the sound source in terms of three ways. For example, it's just by 2 to 3 degrees different, depending on the person's hearing. It could be, for example, you could say 70 degrees. The sound is coming from an angle that is 70 degrees, or 69 or 71. So it is, in reality, it's about just 1 degree higher, 1 degree lower, but it is within 3 degrees. So it's really accurate. And vertically, you do a different system, and then you put the vertical with the horizontally. I did pinpoint the sound source exactly, and you understand how far it is from you based on the pressure and the length of the wave, and all of this. So the maximum delay between one ear and another is 600 microseconds. If you divide the second into a million units, that is 600 units out of that will be the difference between the time it takes the sound to go from one ear to the other on average, because some people have larger heads than others, children have smaller heads, and so on. So when I say low frequency sounds, we mean low pitch sounds. Low pitch sounds are evenly received by the ears and perceived, but high frequency sounds, when the sound reaches kind of basically 2000 hertz or so, they produce differences, or called sound shadows, in terms of intensity, loudness. And because loudness goes with pitch, high pitch sounds tend to be softer, to require more energy so that you can make them louder, and low pitch sounds tend to travel farther away and to fill the space and to stay longer in space. So basically, high frequency sounds provide us with cues about horizontal localization to enable us to understand to identify the angle, right, front, and so on of the sound. So what I want you to understand from this is that the system, and basically different stations along the brainstem, they calculate information about the intensity of the sound, about loudness of the sound, and information about the length of the wave. And that gives us, if you know the length of the wave, you know how long it takes the sound to come to you. And then you can calculate basically exactly where the sound source is by feet, by meters, whatever it is. So the auditory nerve, now the neurons in the auditory nerve fire in synchrony with the sound wave that's coming from outside. If you trace one sound wave that hits the eardrum is going to mimic exactly, instead of the sound wave for example, going back, it goes back and forth like that, it will make the eardrum go back and forth, exactly the same pattern. And that is repeated by the bones, and that is repeated then by the fluid as the fluid goes up and down. And then that pattern of the sound wave involving pressure, basically, pressure up and down like this, that pattern is translated into a firing pattern by the hair cells inside of the cochlea. So it mimics exactly this. So if the sound signal, say, has 100 frequencies, or 100 cycles of vibration, then the eardrum is going to vibrate 100 times. Then the fluid in the cochlea is going to vibrate 100 times. And then the this neurons or the hair cells, which are basically the tips of the um, auditory nerve, they are going to fire 100 times as well. If you make the signal a signal that's coming in at 2000 hertz, the firing will be exactly 2000 times. And when you look at words that we say and sounds, they have a pattern. When you say escalator, that has a particular pattern of sound waves coming in and having a certain shape. And that pattern is when you hear the word over and over and over, and it causes a firing pattern, that then becomes associated with the word escalator. And this is how we learn. We hear something over and over until we make the pathways fire exactly in the very same pattern, and that is the pathways will remember that pattern, and this is learning. This is how we learn. Low frequency sounds induce firing simultaneously, but high frequency sounds produce intensity differences because one ear is going to be more aware of the sound, getting it first than the other, and that is going to give us cues about horizontal location of the sound. So high frequency sounds enable us to do horizontal scanning. Now, this is important. It has implications for learning. Musical sounds, when we say harmonic sounds, that means sounds that follow a specific pattern that keeps the same it has a pattern that repeats itself over and over in different ways. It could be a complex pattern, it could be a simple pattern like this, or so you can do any pattern. So musical patterns that are systematically repeating themselves, they cause the auditory nerve neurons to fire in phase, to fire exactly to repeat that pattern. And it becomes pleasant because now the system knows what it is going to do, and it can predict it, it can anticipate it, it becomes pleasant. And this is why music is enjoyable, and it is connected to our memories and our emotions and so on. It relaxes us because, again, you just sit there and hear the same kind of pattern, the same as a water cascade. It repeats the same pattern. And when you think about speech is a system that depends on patterns, depends on melody, depends on what we call intonation. Intonation you have a tone, and then you you create waves as you go in a systematic way. The better and the more the more kind of musical the words become, the more pleasant they are. And this is why singing and poems and songs are so valuable. They just move people and make them, and that is because, again, they get the best kind of form of speech, so that it makes it reach its best patterns, so that becomes musical. But speech itself is musical. So when musical sounds combine and produce melodies, they elicit regular periodic firing in the auditory nerve, in which the most common interval between action potentials of the neurons corresponds to the periods of the pitch. The period is the time it takes, how long it takes to make a sound wave. So you know now that the auditory nerve, the neurons and the auditory system translate the pattern of the sound wave into a pattern of firing along the pathways, and these patterns, they become the pathways remember these patterns and they associate them uniquely with individual words. And this is why when you think about a word, the same pathway just starts to flash. And when you hear the word, exactly the same pathway begins to flash because that pattern is unique to that particular word. Now, what happens when we do all these rhymes early in childhood, when we make kids, make their own rhymes and find out, so basically phonics, and also doing rhyming activities, this is basically building the patterns along the auditory pathways. It is a very effective strategy, especially in younger children, and it is going to facilitate learning of many skills that depend on, like literacy skills, and other skills that depend on the auditory system. When the sound is not harmonious, we call it aperiodic. That means there's no pattern to it. That is basically a bunch of signals that are so different and all just merging together, they become a bunch of noises. And noises become disruptive. That the nervous system doesn't know what to make out of them, and it tends to ignore them, and they interfere with the signals that we would like to hear, and they create a distraction. So this is why in a noisy situation, children or adults will be at risk for not learning as well as they would if the situation is more optimal. It doesn't have noises that distract. So these were the implications, but I'd like you to think about more implications about the musicality and how musical sounds, wherever you find them, are going to enhance learning, and how they enhance our ability, the brain's ability to make patterns, and how they contribute to learning, and also the effect of noises. So I'd like you to think about implications for the students that you have or you have worked with, or also recommendations along that. So central auditory processing. Let me see. Yeah. We'll take a signal and we'll trace it. If you expand this, you're going to be able to see the steps. But I'm going to explain in simple language. You hear a signal that comes in until it reaches the cochlea, and then the cochlea, the sound wave is converted into an electric pattern of firing that mimics the timing and mimics the number of sound waves that we hear. Then all of these signals are going to be channeled. They will go through the auditory nerve. And the auditory nerve is also organized in a very particular way based on high pitch, low pitch, and so on. And as it goes into the brain stem, then there are particular stations here, especially a place called the cochlear nucleus. The word cochlear nucleus comes from a cluster of neurons that are specialized in receiving signals from the auditory nerve coming from the cochlea. So this is why it's called the cochlear nucleus. And it is part of the structure of the brain stem that is called the medulla, basically on the very top of the medulla, where the nerve enters the brain stem. And then it goes along the auditory pathways to be processed. But I wanted to emphasize what is meant by tonotopic organization. Tonotopic means specialized in particular tones. The cochlea, if you imagine the cochlea like a piece of dough coiled twice, 2.5 times, and then uncoil it. As you uncoil it, you are going to find that the very top of it is specialized in the lowest frequencies, and the very bottom of it is specialized in the highest frequencies or the highest pitch. And you could see now on this the diagram here, and it shows you, for example, how these high pitched sounds are coming, and as you keep moving to the top, it becomes lower and lower and lower until you reach 25 vibrations or 20 vibrations. That's the lowest pitch sound that a human being can hear. That means if I move my hand 20 times per second, I don't think it's possible, then it will make a sound that a human being somewhere is able to hear. Now, on the other end, in the base of the cochlea, it detects sounds that are 20,000 times, 20,000 vibrations in 1 single second. And that is like so high pitch. And these are the limits of, for us. Bats can hear above that, and other animals can hear also above that and also below the 20 times per second. So every segment of the cochlea, if you imagine the cochlea as a spiral staircase, you can think about every that spiral staircase being say 20,000 steps, and every step is going to have one particular, for example, specializes in one particular frequency. So as you could see here. So as the auditory nerve enters into the brainstem, it goes into an area that's between the medulla and an area called the pons. So you could see it here. If we slice this, the top of the medulla, you slice it, you are going to come to this cross section here. So here are the cochlear nuclei. There's one here and one behind it. You don't have to worry about them. One is called dorsal, one is called ventral, like front and back. And so this cochlea, as it goes in, you have out of it, you have 4 pathways. It crosses over to the opposite side. You have 1, 2, 3, 4 pathways going up, and then 2 pathways going to the same side. So this ear, 2 pathways go to the same side here, and then but 4 pathways cross over to the opposite side of the brain stem. So they are all ascending because they bring signals, and then you count and say, oh, that is not 4, that is 5, or that is not 2, this is 3. Blue means the signal is coming down. So blue means this is a feedback loop that comes from this area down, so that it can tell the cochlea what to do if it needs to amplify the sound or not. The cochlea, remember the outer hair cells? The outer hair cells can amplify the sound up to 100 times. So if the sound is compromised, it's going to amplify it. The sound, these hair cells will amplify. Also, in other areas like the thalamus has a place here, a part that we'll speak about, that also has the ability to control loudness of the sound. So the cochlear nuclei, basically, these areas here, they enable us, they can collect information about the time, the difference between one ear and the other in terms of time that they receive the signal, and the frequency, the pitch of the sound. If you know the pitch, you know how long the wave is, and then you remember, if you have the vibration rate, you can calculate the distance exactly, perfectly. You say this is about, this number of meters or feet. We know it instinctively. Sometimes you might not estimate it in words correctly, but we know it instinctively when we hear a sound coming from a certain direction. And there are specific nuclei, neurons in the cochlear nuclei that enable us to detect low frequency signals in a horizontal plane, and also to detect other groups detect high frequency. So it's very specialized. And again, some of the pathways go to the same ear. To the same side of the brainstem that's the same as the ear itself, and also to the auditory cortex itself on the same side, but just only two. And then 4 pathways cross over and they go to the opposite side. And in the process, there is integration, or the two signal from the 2 ears is kind of integrated. But the sites that integrate include a very important station here called the superior olivary complex, or the superior olivary nucleus. Nucleus, again, is a cluster of neurons with their cell bodies, and that is not located in the cerebral cortex. And nuclei is more than one. So these are the olivary nuclei. Then the signal from the olivary nuclei add more information as they receive that information from the lower centers. They add more information, they process it more, and they keep sending it up to other structures. So also the cochlear nuclei have the ability to identify sound patterns, to recognize them. If you have heard it, then it can help you identify if that is the sound that you have heard. So the signal goes from the cochlear nuclei, goes to the superior olivary nuclei, or nucleus complex. And then from there, it goes, all these pathways converge onto an area called the inferior colliculus. So the inferior colliculus, that is part of the midbrain, is going to send signals to an area in the core of the brain called the part of the thalamus here. We spoke about it before. But a particular area of the thalamus called the medial geniculate body. And that is going to process the signal in many kind of refines it, and it amplifies it if it needs to be amplified. And then finally, the signal goes from there to the auditory cortex that is here above the ear. There is a pathway that I mentioned here, the blue, that goes from the olivary nucleus down to the cochlea, and it's called the olivary cochlear, or pathway. And that, again, if the signal is compromised, if the signal is not coming really well, that area is going to send a command down to the cochlea and say, no, give me more amplification. And then the cochlea is going to, and if the sound is very loud, it is going to suppress the functioning of the cochlea with the hope that it can protect it, because an extremely loud sound can cause hearing, can damage hearing. So these are protection mechanisms and mechanisms to amplify and enhance sound. So again, the function is to increase, function of this loop is to increase representation of signals and noises. For example, by amplifying a signal, in a cafeteria, for example, or a party, that you kind of are struggling to hear the person. There's so much noise. So that loop is going to enable the cochlea to maximize its functioning, so you can focus more on the sound that is compromised. It also reduces sensitivity of the cochlea and protects it against from damage that could be caused by loud sounds. So this ends our first section, and that will be followed by the second one. Thank you.